Hello everybody, in this video I'll be showing usage of Windows Debugger for kernel and user mode debugging. We'll be walking through system structures like EPROCESS, KPROCESS, ETHREAD, KTHREAD, thread environment block, process environment block, and their using. I will give you some brief information about these structures and their differences. All this walkthrough document is available on my GitHub page. You can see it here. The link is available below this video. Some information covered in this video. You can get this information in awesome reverse engineering course, which is called malware analysis course from made by Hasherezade, and you can get this course on her GitHub page. It's here. The link to this course is also available below this video. And in this video, I'll be covering especially the module 1 of the malware training of made by Hasherezade, module 1 and chapter 3, which covers processes, and module 1 chapter 4, which covers WOF64, so running 32-bit code on 64-bit processor. Some user links are below this walkthrough document. User links to the Hasherezade's malware analysis course, and link to common Windows Debugger commands, which is quite a useful source of information. You can see it here. And interesting tools I'll be using. So Windows Debugger Preview, you can get it on Microsoft Store. Windows Debugger the same, and XNTSV, which is available here, and shellcode 2exe. Okay, shellcode 2exe is I'll be using this tool only for wrapping the shellcode code to executable format, and XNTSV is a very useful tool. You can grab it on GitHub page here. And this tool or program is for detailed viewing of system structure, which is basically what we will be doing here, thanks to the Windows Debugger. But I will show you how to reach to get the information about system structures thanks to this tool too. It's really easy to use, and it has a graphical user interface. It's and you can get very interesting information from this tool. Well, let's start. For all this exercise, we will be using our generated shellcode, 32-bit and 64-bit. We will generate it with massive Venom, which is a part of Metasploit framework. After we generate the shellcode, we will wrap it to exe file to make it simply debuggable. For this purpose, I'll be showing the shellcode 2exe tool. And after that, we will compare the produced wrapped shellcode in EDA, and we'll be focusing on API resolving and imports retrieving. Basically, the parsing of structures like thread environment block, process environment block, and others. Well, we can jump to the generation of the shellcode. Copy this command. All these samples, the shellcode samples and the wrapped exe file, are available on my GitHub page. If you check it here, yeah, so generated shellcode available here, shellcodes, and wrapped to exe here. So jump to the Metasploit framework and generate the shellcodes. here. Basically, the MSV Venom will be using the payload Windows exec, which means it's using the WinExec function of kernel32 to run a calculator and produce. It will produce the 32-bit shellcode. We have to copy the command also for 64-bit shellcode. Yep. And for 64-bit shellcode. Basically, this command does the same as the command before, but only generate the 64-bit shellcode. I'm using this kind of shellcodes because the interesting part is that most of the shellcodes are getting or resolving API functions via parsing the thread environment block and process environment block structures. It's heavily used in shellcode, but it's also used in some kind of malwares which are trying to hide the API functions which are using because the malware doesn't want to have it in the import section because it's easily detectable with deterministic signatures and other stuff. So it's using basically it's the malware is implementing the dynamically API resolving, and the API resolving should implement this kind of resolving. I will explain later. Yep, the second shellcode is generated. We can see it here. These are two shellcodes. I can delete them because I already prepared them in different folder. It's here. And now it's time to wrap it to exe files. We will be using the shellcode to exe, and the command for it is here. Basically, it means shellcode to exe, 32-bit architecture, input is a 32-bit shellcode, and output is a 32-bit executable file, the wrapped shellcode. The same we have to do for the 64-bit shellcode. And it's done. We can check it. And our executables are here. I can again delete them because I already prepared them here. So now it's time to compare them in EDA. Check how they are performing the parsing of thread environment block and process environment block structures. Let's jump to EDA. I already prepared the EDA database of these shellcodes where I implemented appropriate structures. So 32-bit and 64-bit. Yep. So this icon, hide it quite a bit, and this will be 2. Yep. So here is a comparing of 32-bit wrapped shellcode and 64-bit wrapped shellcode. You can see immediately that's a 64-bit code, and here it's 32-bit code. And here you can see that I already applied the structures. But if I didn't apply the structures, it will look like this. And this. You can see that the 32-bit code is pointing to FS. FS is segment register, and the segment register FS is pointing. It's used only with 32-bit code, and GS register is used with 64-bit code, and both these registers on the specified architecture, 64-bit, 32-bit, they are pointing to thread environment block structure. You can see it here in the documentation that segment registers FS is 32-bit and GS 64-bit. They are used to point to operating system defined structure, manage thread specific memory, and it means thread environment block. In thread environment block on FS segment register offset 30 and GS segment register offset 60, they are pointing to address of process environment block. But the difference is that the 64-bit, the GS on offset 60 is pointing to process environment block 64-bit, and FS segment register on offset 30 is pointing to 32-bit process environment block structure. And here you can see different kind of offset, and here you can see that the offsets are different, but this code is doing the same, exactly the same, but this is for 32-bit and this is for 64-bit. So if I again apply the structures, you can see that here is the pointer to thread environment block, process environment block. The address is saved here, and here is the process environment block LDR address here, and here is the process PEB LDR data, and in memory or module list link. Other is full DLL name buffer, and other is full DLL name maximum length. And if you check it here, it's the same. And we will confirm it later in Windows Debugger, and I will explain it later why the malware is using this kind of process environment block and thread environment block structure parser, because it wants the shellcode wants to get the name of the module which is in the buffer in here, and it will compare it with some module name, and after it retrieves the module name, it will find the base address of the module, and it will start to find other structures to find appropriate API function name, to save the address of this function, and later it will be dynamically called. And that's all from EDA for now. So we can close it, close the one instance, and the second one. Well, I explained the segment register, what does it mean and why are they used. I will show you also later in the Windows Debugger, and some brief information about system structures. EPROCESS, KPROCESS, ETHREAD, KTHREAD, thread environment block, and process environment block. So basically, thread environment block and process environment block can be accessed from user mode, contains process and thread specific information. They contain information which are used, for example, with image loader, heap manager, and they have to be accessible from user mode. So they are accessible from user mode. EPROCESS and KPROCESS structure can be accessed only from kernel mode, and they are really important because they are representing the process object in kernel. ETHREAD and KTHREAD can be accessed only from kernel mode again, as the EPROCESS and KPROCESS, but they are representing the thread object. EPROCESS, which is in kernel, contains pointer to KPROCESS structure and to process environment block. Yeah, you heard right. EPROCESS contains also pointer to process environment block structure, And the process environment block structure contains information which are exposed to user mode. ETHREAD contains pointer to KTHREAD and structure KTHREAD structure, and KTHREAD structure contains pointer to thread environment block. And again, thread environment block contains information which are again exposed to the user mode. So EPROCESS, KPROCESS, ETHREAD, KTHREAD, these are structures which are only accessible from kernel mode, but they have also pointers to process environment block and thread environment block, and these two structures are accessible from user mode. There is one quite a tricky thing. 64-bit processor on 64-bit processor architecture contains one 64-bit structure of PEB and one 64-bit structure of the thread environment block. That's nothing suspicious. 32-bit processor on 32-bit processor architecture contains one 32-bit structure of process environment block and one 32-bit structure of thread environment block. Again, nothing suspicious. But here, be careful, because 32-bit processes on 64-bit processor architecture contains one 32-bit structure of PEB and one 64-bit structure of PEB, and one 32-bit structure of thread environment block and one 64-bit structure of thread environment block. And that's all because of 64 emulation. You can see the explanation here, which is a picture from Hasherezade Windows malware analysis training. The link is available here. And here is the brief information what I covered here. Basically, Windows 64-bit processes on 64-bit architecture have only one 64-bit thread environment block structure and one 64-bit process environment block structure. 32-bit on 64-bit processor, 32-bit processes have 4 these structures. Yeah, and that's because of emulation of 32-bit code. Because to make it possible to run 32-bit code on 64-bit processor, there has to be performed some kind of emulation. It's quite a sophisticated process, and because of that, the process has to have 32-bit structures and also 64-bit structures. And here I write simple explanation. It's quite subjective, so I write this explanation because I got quite many questions about EPROCESS and KPROCESS. What is the differences between these two? Because they are both in kernel, but the KPROCESS, the K is like for kernel and the E is like for executive. So why they have this kind of names and other stuff? So I want to explain it quite in brief. So when you are creating process, both the kernel and executive subsystem want to track it. You can see below. This is a picture from Windows kernel programming by Pavel Josifovich. You can see here is the layer of executive subsystem, and here is the layer of kernel subsystem. Both are in kernel mode, in kernel space memory. So when we are creating process, both the kernel and executive subsystem want to track it. Kernel, for example, wants to deal with the priority, and affinity of the threads in the process because that's going to affect scheduling. Yeah, that's only example. The executive subsystem wants to track the process, for example, because of security. Executive subsystem wants to associate a token with the process, so security checking could occur. That's why, for example, EPROCESS holds the token. The structure that the kernel uses to track the process is the KPROCESS. The structure that the executive subsystem uses to track process is EPROCESS. The KPROCESS is the first field of the EPROCESS, so the executive subsystem allocates the EPROCESS structure and then call the kernel to initialize KPROCESS. Again, both structures are part of the process object that represents the instance of the user process. Very important. Both are allocated in kernel memory space. the names, if I understand it well, comes from names of subsystems that interact with these structures: EPROCESS, executive subsystem, KPROCESS, kernel. Okay, let's jump to our settings for the exercise. We will have to set up the kernel debugging with the Windows Debugger preview in host, and we will be debugging guest VM. In the guest VM, we will have user mode debugger, Windows debugger, because I want to show you that the Windows debugger in user mode can also read information from the process environment block and thread environment block because they are accessible from user mode. And the other structures like EPROCESS, KPROCESS, ETHREAD, KTHREAD are only accessible from kernel mode. So for this purpose, I will be debugging the kernel. So first of all, we have to jump to our guest VM and start a command prompt as an administrator and run this command. First of this command prompt. Okay, with this command we basically enabled the debugging, kernel debugging, and we jump back, and with this command we basically set the debugger port. The COM1 is we are assuming that the COM1 port will be used. Well, that's all, and now we start to shut down the VM. Now we have to go to the settings of the VirtualBox VM and set here the appropriate settings for the Windows kernel debugging. We can jump to that. Yeah, here is my virtual machine. Go to settings, and in settings go to serial ports. Port 1, enable serial port, COM1. Port mode will be host pipe, and this will be unchecked. And here we have to fill the name pipe, host pipe. Yeah, and I already prepared this pipe. Click OK, and that's it. Now, before we start the VM, I want to show you one thing, because later we will be using the XNTSV application, which I already point here. And for this purpose, this program is using a driver which will be loaded, but the driver is unsigned. And to be able to load unsigned driver, we have to edit advanced boot options. We can jump to the advanced boot option with the F8, and we have to disable the driver signature enforcement. So go for it. Start VM, and during the boot, press F8. Yep, and here is the disable driver signature enforcement. Yeah, it's only for the XNTSV program, so we will be using later, so I want to have it prepared. Now it's time. We can prepare the host for kernel debugging. So we jump to the Windows Debugger preview, and we have to configure it to attach to the kernel of our VM already configured. So jump to the Windows Debugger preview. Go to File and start debugging options and attach kernel. And here in COM tab, we have to check pipe, reconnect, reset 0, baud rate, as we already filled in VM, and port is our specified named pipe, and we don't want to break it on a connection, so uncheck this. And that's all. We have to wait until our VM will start. Yeah, it's here. So jump to the Windows Kernel Debugger, Windows Debugger Preview, and click OK. And we can check if we successfully connected, attached to the kernel. We can see the debugger is running. If we press a break, we can, for example, list all processes and check if everything is working okay. We can print all processes like this. 0, 0, 0. Basically, we will print all processes running in the VM, and we will print only brief information about these processes. And we can check that it looks like it's everything working. So now we can press go to make the debugger again running and detach, because we'll be using the Windows Debugger preview later. Okay, now it's time to jump to our VM and check the parsing of process environment block, thread environment block of our red shellcode to exe file. So jump to our VM and start the Windows Debugger 32-bit and Windows Debugger 64-bit. You can see that I already prepared the wrapped shellcode 32-bit and wrapped shellcode 64-bit, the XNTSV application 32-bit and XNTSV application 64-bit. So let's run the 32-bit wrapped shellcode. Go to File, open executable, and find the wrapped 32-bit shellcode here. Open. It looks like everything is okay, no problem with symbols. And now we can jump to our entry point. We will do it like this in this assembly view. EXENTRY. Some kind of freeze. Yep, we are there. And we are not on our entry point, so again, EXENTRY. Yep, and we are here. Now put a breakpoint there, BP, and this variable. And the breakpoint is set. Now go to debug and continue to reach our set breakpoint. You can see it in, if you check the EIP register, yeah, we are on our breakpoint. Now we don't need this window, so let's close it. And leave only the disassembly view and command view. You can zoom it. And we can zoom it this too and clear the command window. Yeah, and we are prepared with 32-bit Windows Debugger, debugging the 32-bit wrapped shellcode. And jump to the 64-bit Windows Debugger and do the same. So basically, file, open, executable, find the 64-bit rep exe file, open. Yeah, we stopped on the system breakpoint and go to the entry point. Yep, we are there on the entry point, and put a breakpoint there again. And press debug and continue. Check the RIP register, which will be pointing to, yep, no, here, RIP register. Yeah, we reach our breakpoint. So now is the time again, close all windows because we don't need it anymore. Yep, and we can again zoom it a little bit. And zoom it here too. Okay, and clear the command window. We can view and full screen, switch to full screen, it will be better. Yep, and we can jump. We can compare now. This is the 32-bit, and check the processing of the thread environment block and process environment block. I already pointed in IDA. Yeah, the FS segment register and the offset. It's different than here, but it does the same. GS segment register in 64-bit, and the offsets are different to 32-bit code, but it does the same. So let's jump to our 32-bit, and we will start with that. So we are on the entry point, and we can start to basically find the same information. What we'll find our shellcode in memory via these instructions. So let's find the thread environment block, because FS segment register is pointing to thread environment block, and find the offset of 30, which is pointing to process environment block. So go like this: DT and DDLL, thread environment block structure type, and address is current thread environment block, and we can go for it like that. Yeah, press OK, and we are in our thread environment block structure for our current 32-bit process, 32-bit structure of thread environment block. And we can check it on offset. 30 is the process environment block, and this is the address of the process environment block. So we can jump to the process environment block structure for our current process. Basically, we can do it like this to specify that we are interested get me the type of process environment block, and the process environment block is on this address. Okay, and we are on the process environment block structure, which starts here. And check the another offset, which is here, and it's a C in hexadecimal. C in hexadecimal is pointing to LDR, which is type of PEB LDR data. So we have to again check or copy this address, and we can view this structure PEB LDR data on this address like this: DT and TDLL, and the structure type is PEB, and press tabulator, it will find the appropriate structure, and here, and the offset is here. Okay, and we are on the structure PEB LDR data for our current process, and here is our offset 14. 14 is in memory order module list, and you can see that it contains a list of many entries, and each entry is type of LDR data table entry. So we have to specify this type in the command, because we want to see the structure LDR data table entry on this address, because it's our first, which is searched here. Copy this offset and go like this. ET and TDLL, and the structure is LDR data table entry, and the address of first entry is here. Press OK, and you can immediately see that we are in the first entry of the list, which is type of LDR data table entry. And we can see that other offsets are both. We can see, because this goes to EDX register, and EDX reference here and EDX reference here. So both of these are saved from this structure, and you can see that it's an offset of 28 and 26, but we can't see here 28 and 26 because it's a part of this. It's hidden in this structure full DLL name, which is type of Unicode string. So if we want to view this structure, which is type of Unicode string, we could go for it like that. DT and DLL, and structure type is Unicode string, and the address is this plus appropriate offset. Appropriate offset is 24. And press OK. And what we got here, we can see that 26 offset is processed, and it's basically 24 plus 2, and 2 offset is here, maximum length. So maximum length goes here, and 28 is 24 plus 4, and it's buffer. So basically buffer is pointing to our module name. In this case, it's the first module name in memory, and it's our main module, the red SC32 exe file. Yep, and how does it all work? Because, for example, the shellcode is this shellcode exactly is finding or searching for WinExec API function, which is part of Kernel&User DLL, and basically for this module is not Kernel&User DLL. So how does the shellcode find the Kernel&User DLL? It basically goes like this, because it finds this structure. Find the full DLL name, the buffer name, compare it with Kernel&User DLL, and it's not equal because this is the red SC32 exe. So it only process another entry in the list in lower order links in this structure. So if you copy this, it will be pointing to another module in memory. So here, and the structure of rep SC32, which is in LDR data table entry type, a part of the list, is the in lower order links first entry is pointing to another module and memory, and it should be NTDLL, exactly, NTDLL. Now again, in lower order links, check another, and NTDLL will be pointing to another module in memory. So if you copy that and press through it like this, you successfully find the Kernel&User. And now the shellcode will find the DLL base, find the base address in memory, and start to parse and process the executable structure of Kernel&User DLL. And why does it do it like that? Because it tries to find the export section and try to find the export API functions of Kernel&User, and it try to find API function name WinExec in this example, and address of the WinExec in memory. And after it finds the name and the address of the WinExec, it save it in some memory address, and after that later it will be dynamically called the WINExec in this case. Well, that was all for the 32-bit, and we can jump to the 64-bit. Basically, we will do quickly the same what we did before. So again, dt ntdll, structure type is TEB, thread environment block, and address is TEB. Okay, we are on the thread environment block 64-bit structure, and we can see that offset is 60. So 60 is pointing to process environment block in 64-bit structure. So we can copy this address and go change it like this. We can we want to structure type of process environment block, and here is the address. We are on the process environment block and check the another offset is 18. So find the 18, it's LDR and it's pointing here. And type of PEB LDR data. So go like this, PEB LDR data, address is here. And we are on the PEB LDR data, and the offset, our offset is 20, and 20 is in a memory or the module list. And we already know that this list entry, each entry is type of LDR data table entry. So we want this address. Because it's the first entry. And go for that like this, LDR data table entry and address, bam, and it's here. And check the offset 50 and 48. You cannot see here 50 and 48, you can see only the 48 because the 50 and 48 are part of this structure full DLL name. Again, we already saw it in a 32-bit process. So to be able to get the Unicode string structure, we have to go for it like that. Unicode string structure type, and the address is this plus offset, and offset is in this case 48 in hexadecimal. Yep, and we are here. We can see that the 48 plus 2 is 48, so offset 2 is maximum length, and 48 plus 8 is 50, and 8 offset is here, so buffer, which is pointing to the name of ret SC64, which is the first module in memory, and it's our main module. We already saw that. And that's it. We leave it like that because we need these processes in Windows Debugger, in kernel debugging. So jump to our kernel debugger. The processes are running. They are attached to these debuggers. Jump to the Windows debugger. Go to File, attach to kernel, and OK. Debug is running. We can stop that or pause. There, pause it, and we want to investigate it. First of all, I already show you that we can list all processes like this, and 0 and 0 because we want to all process with only brief information about this process. And we find here some of the ret, yeah, here ret SC64EXE, and we immediately can see here is some address, process address, and basically this is the address of EPROCESS structure in kernel. EPROCESS representing the process object. If we want to investigate the EPROCESS structure of the process ret SC64, we can go for that like this. EPROCESS structure type, and this is our address of the EPROCESS. And we are here. And where we can see only the information I already pointed. because the first element in the EPROCESS structure is pointed to KPROCESS, and part of the EPROCESS structure is also process environment block here, which is exposed to the user mode. And we can see here some interesting information in EPROCESS structure, unique process ID, and token information, as I already pointed that it's used with the security subsystem. It's really heavily used with exploitation, that you can basically steal the token of some more privileged process, and basically you can patch the token in your process, and you basically do the privilege escalation and other stuffs. If you want to search, if you want to view the structures of KPROCESS of our process, you can click. The Windows Debugger preview has quite a big advantage because it's more clickable. You can click on it, and you are on the KPROCESS structure. You can see that there are more information relevant to kernel subsystem. You can see here the affinity, you can see here the priority somewhere here, base priority, process flags, thread seed, and other stuffs, cycle time, kernel time, user time, more kernel subsystem specific. And if you want to find the ETHREAD and KTHREAD structures, I will show you one thing. You can basically again install processes, and we were interested in this process, and its process is unique process. Its unique process ID is here, A44. So just copy that and modify this command. You can specify the process ID here, and we will not paste here 0 but 7, and it will give us far more information, not only brief information about this process. And one of this information is also thread object and its address. Done. You can see it here. We can see that it's the image wrapped SC64, and what we got here, thread object, and this is the address of thread. And what it basically means, it means that it's address pointing to ETHREAD structure. So if we want to investigate the ETHREAD structure, go like this, ETHREAD address, and you are there. And what is here, you can see that there are plenty of informations, but what I already explained to you is that the first element of ETHREAD structure is pointed to KTHREAD. And KTHREAD, if you go to the structure KTHREAD, you can go and click again. You are on the KTHREAD structure, and what is interesting part of KTHREAD structure is also the thread environment block. Again, thread environment block is a structure which is exposed to the user mode from the kernel. And that was the part of Windows kernel debugging to show you the structures in kernel, the EPROCESS, KPROCESS, ETHREAD, KTHREAD. And now it's the time for shining another tool. We have to continue and detach. Jump to our VM. And now is the time to show you the XNTSV tool. We can see that these the debuggers are still running. The wrapped SC32 and SC64 exe file are still running. So let's jump to the XNTSV application. we can run it. We already disabled the driver signature enforcement, so there will be no problem with the loading of unsigned driver, which is basically used. You can see the driver here. It's used for memory access to read the kernel system structures of a specific process. And basically what you will see with this tool is all what we already did with Windows Debugger user mode, Windows Debugger kernel mode, and it's really easy of use, and you got plenty of useful information from this tool. It has nice graphical user interface. You can switch, close that, you can switch between user mode and kernel mode. In user mode you only get the process environment block and thread environment block and address structure, which are from this structure. And in kernel mode you can grab the ETHREAD, KTHREAD, EPROCESS, KPROCESS structures from the kernel memory for the specific process. So first go to user mode, and in user mode find the, for example, red SC64 and start. You can see the process and thread. Process, if you go to process, you can see that you are immediately in the process environment block structure, and there are plenty of information. And if you go back, you can go to the thread, and you are immediately in thread environment block structure. And if you remember how the shellcode was parsing the thread environment block structure to reveal the process environment block structure, to get the in-memory loader module list, and to get the buffer and max length, you can go basically here. You can do basically here the same. You can find the offset 60 is a process environment block because we are in 64-bit process, and click on it. And if you remember the offset 18, it was LDR. Go for it. You are in the structure type of PEB LDR data, and here it was the in-memory order module list, structure 20. If you go to Flink, you are on the first element, and if you find the offset 48, it was the full DLL name, if you remember. And if you go for it, you can see here, you can immediately see here that it's pointing to the module name. But if you go for it, you can see that first element in this structure is length, another is maximum length, and another is buffer. Here is not exposed the real module name. But if you wanna be really I don't know how to say it in English, so if you want to be painfully so just copy that buffer, which should point to our module name rept SC64, and to confirm that, jump to, for example, process hacker, and go to 64 process and memory. Search for the offset. I already copied, and you are here. You can see the offset is 2B is the, and 3A 8E is the offset. Go for it. And if you go like this, go to, and here like that, okay, you are there. It's starting with the C, and what we got here? You got here the module name of our investigated executable, investigated process. Yep, so we confirmed it. Now we can close the process hacker and switch to the kernel mode. We are still in this process, kernel mode, and go start. And you can see here process and thread. Basically, process is pointed to process object, and process object is represented with the EPROCESS structure. And you can see again, first element in EPROCESS structure is KPROCESS, and here is somewhere the process environment block, here, which is exposed to user mode. And if you go to the KPROCESS, you can go on it like one click, and you are in the KPROCESS structure. If you go back and want to investigate a thread, like ETHREAD structure, kernel structure, you are in ETHREAD. And first element of ETHREAD is KTHREAD. And if you click on the KTHREAD, There should be somewhere the thread environment block structure. You can see it here. Export again to the user mode. And that's all. That was all about XNTSV. Really useful tool, and it's really quick for use and easy for use. You can get far more information, and it's really good for learning system structures. If you are not so familiar with Windows Debugger, because it's a command line debugger, so it's not so easy. But with this tool, you can investigate the system structure easily. And that's all. That's probably all what I wanted to cover. So I hope you enjoyed it, and thank you for watching.